Maybe one of my favorite thing about Tandem is that we're really pushing the boundaries of a whole community. Just by scaling these simulations up to the size of supercomputing applications, we're able to run models that nobody else has seen before. We have short-term predictions of the weather. We don't have short-term predictions of earthquakes. And one of the main reasons is that we don't have a good understanding of the physics that are driving earthquakes. And without understanding the physics, it's really tricky to come up with predictions. So one of the things that we hope we can contribute is tackling the physics that drive all these processes, but then also come up with direct products that can help seismic hazard assessment and mitigation of seismic hazards by, for example, modeling more realistic earthquake catalogs that can be used for hazard maps, coming up with rules of how earthquakes could jump from fault to fault, or come up with realistic ground shaking that is more detailed than the few data points we have from real earthquakes. My name is Alice Gabriel. I'm a guest professor of earthquake physics at LMU Munich in Germany, and I'm an associate professor of geophysics at the Scripps Institution of Oceanography at UCSD. And I'm one of the PIs of the GEES project. So Tandem, in difference to SEISO, is focusing on sequences of earthquakes. So we're trying to model the full seismic cycle, what we call the seismic cycle. So if you have a fault, so a geological structure that is producing earthquakes, it's usually not just producing one earthquake, but it's producing several earthquakes over centuries, so several hundreds to thousands of years. And this is the time scale that we're trying to capture in our Tandem simulations. These kind of faults, they also don't only produce earthquakes, but they can also creep. So that's not something scary, that just means that they're slowly moving without producing earthquakes. It's really interesting to understand how this transient movement connects to earthquakes and what happens after an earthquake. When will the next be? Will it be larger? Will it be smaller? How do these faults live throughout the seismic cycle? So that's what this code is focusing on. What's different in Tandem is that we're including the physics of earthquakes due to friction, actually. It's boiling down to mechanics. A lot of the complexity of earthquake behavior is due to the way that the rock is breaking, and then during the movement of the earthquake there's friction between the two sides of the fault, and that's highly nonlinear. So friction is actually a Nobel Prize topic. It's one of the things that is really difficult to figure out. And then earthquake friction is even more difficult because we can't measure at 20 kilometers depth what happens. So it includes this kind of complicated friction plus realistic geometries of faults, topographies of mountains, and the whole structure of the subsurface. And it uses supercomputers to put all of this together. What's really innovative is it's using PETSI, so that's a well-established library that's it's a finite element library that's tuned to use supercomputers. So it's using some established libraries that make it very efficient on large machines. It's open source. There's very few open source codes actually that are usable. And we're really trying to tackle large problems that are not feasible without supercomputers. So we see our focus in trying to do simulations that are not possible on the laptop scale. Inside GEES, we are interested in porting Tandem to GPUs. So that is something that is a big topic. So many of the new supercomputers that are being built, they're using GPU hardware, and we will have to adapt the code to be as efficient as on CPUs on the GPU machine. So just being up to date with our implementation. So we've been doing that. We're also trying Tandem out on many different European supercomputers and worldwide supercomputers, but within GEES, we're focusing on the European ones to better understand how it ports and how we can make it more versatile and easier to compile and easier to ship and easier to use, basically.